In this lecture, we will develop the time-independent perturbation theory, right? So, before developing the time-independent perturbation theory, let me show you by using an example what the perturbation mean, right? So, I will introduce you some terms that we will use in time-independent perturbation theory by using this example. So, it is the particle in an infinite potential box, one-dimensional box. So if it is 0, it is 1, it is the x-axis measuring the distance of the particle from the origin, and the y-axis is the measure of potential energy of the particle in this region. So potential energy of the particle before 0, for the points before 0, is infinite, and it after a it is also infinite, and potential energy of the particle in between 0 and 8 is 0, right? So it is kind of potential energy like this. So it is a 0 for the particle in between 0 and a, and it is infinity for other, or you can say infinite otherwise, right? And what you all have done in your previous classes, you have solved the Schrodinger equation this for this particular case. So what you did, you have solved the time independent Schrodinger equation, right? One dimensional time independent Schrodinger equation. So this was the equation which you have solved for this particular case, and what you got was the wave function for the particle in between these 2 points, right? And it came out to be 2 over a, right? Sine of n pi over 2a into x. So that was the situation. Also, you got the energy in the nth state of the particle, right? And what was that? It was pi square h cross square over 2 m a square into n square. So that was the eigenvalue for this particle, and these are the eigenfunctions for these particles. Right? This was the calculation that you all have done in your previous classes. It was when there was no disturbance, it is the isolated system. So in that case, these were the results. But what will happen when now we apply some electric field or magnetic field or any kind of disturbance? So let me suppose that we are applying some electric field, which is constant. Let me suppose that electric field is this epsilon, which is a constant. Now, if the particle in the box is charged particle, so if it is the charged particle, then what will happen is that it will have some potential energy as it was having, but now it will have an additional electrostatic potential energy, right? So due to this electric field, the particle will have some additional electric potential energy, which will be q times epsilon times the distance of the particle from the origin in between these two points. So this will be the additional potential energy of the particle, and because of this additional potential energy, now the Hamiltonian of the particle will get disturbed. So the Hamiltonian of the particle before applying the electric field was, so before applying the electric field, the Hamiltonian was very simple. There is just this potential, kinetic energy term, and there was just this potential energy term in between these 2 points. But now the new Hamiltonian will be the old Hamiltonian, which was the kinetic energy and potential energy as it has, and there will be one more new term, the additional potential energy it has, right? So this is the new Hamiltonian of the particle, right? We can write it like this. So this was the old Hamiltonian, right, which has exactly solvable uh, Schrodinger equation, right? We got these two solutions, this solutions and these eigen energies. for this particular Hamiltonian, right? For this particular exactly soluble Hamiltonian. So it is H naught, which is exactly soluble Hamiltonian or unperturbed Hamiltonian. And there is some perturbation, the disturbance in the system, right? So the new Hamiltonian of the system after applying the electric field will be the sum of the old Hamiltonian and the new perturbation or perturbed Hamiltonian due to some external disturbance. So if this is the situation, first of all, this the external disturbance is called perturbation, and the effect of that external disturbance will be considered by this particular term, which is perturbed Hamiltonian, right? So this is the perturbation. That's why the name perturbation we are using. It is some kind of disturbance, right? So what perturbation theory says, or the calculation we can do by using perturbation theory, we can just use perturbation time independent perturbation theory for the cases where this Hamiltonian is time independent. So first of all, this Hamiltonian should be time independent, right? And the second condition is that its effect must be very small in comparison to the effect of unperturbed Hamiltonian. So in a sense it must just add some amount of energy, or to subtract some amount of energy. It must not disturb the system very abruptly. So if the effect of this particular term is very small in comparison to the effect of this particular term, then we can consider the time independent perturbation theory. And for time independent perturbation theory, this perturbed Hamiltonian must be time independent. This exactly soluble or unperturbed Hamiltonian must also be time independent. That's why this total Hamiltonian of the system will be time independent. So these are the conditions or the assumptions of time independent perturbation theory. So this is the new Hamiltonian of the system, right? And this is the unperturbed Hamiltonian, which was which we can solve exactly. So it is unperturbed Hamiltonian, and this is the perturbation to the system, right? And in this theory, what we want, we just want to calculate the effect of this perturbation on the wave function and eigen energies of the system. So this is an example just to show you what the perturbation is. So perturbation is any external effect, right, which will disturb the system, and this will add some effect to the system so that their eigen functions and eigen energy will get changed. And in this perturbation theory, the main aim we have is to calculate the effect, the change in these uh, wave functions and the energy eigen functions. The assumptions of the perturbation theory, the first assumption is that this HP effect must be very small in comparison to H naught effect, right? If it is not the condition, then we cannot use the time independent perturbation theory. Okay, so this is just an example to give you an idea what the perturbation is and from where this term came. So it is just to show you that. Now we will develop the time independent perturbation theory formally. It is very basic calculation, the simple calculation I will show you to get the energy shift and change in the wave function. So let us suppose let the Hamiltonian of the system is H cap, right, which can be written as, right. So if H cap can be written as H naught plus HP, where H naught is unperturbed Hamiltonian, for which we have eigenfunctions and eigenenergies. So this is the unperturbed Hamiltonian, right? For which we already have the eigenfunctions and eigenenergies. So we can solve Schrodinger equation for this particular Hamiltonian exactly, right? And HP is the perturbation, and it changes the eigenfunctions and eigenenergies of the system, uh, of the system, right? So the first assumption in the perturbation theory is that the effect of this perturbation must be very small in comparison to the unperturbed Hamiltonian. So the first assumption is that the effect of perturbed Hamiltonian HP is very small, right? Then only we can use the time independent perturbation theory. If the effect of this particular term is not the small change in the eigenstate and eigenenergy, then we will not be able to use the results of time independent perturbation theory. So this is the main equation. Now we can write this equation in some other way. Let me write it there. So if HP is lambda times some another Hamiltonian, right, where lambda is a real parameter, right, and the value of lambda is in between 0 and 1, right? So it is 0 when if lambda is 0, then this particular term will be 0, so HP will be 0. If HP will be 0, then the Hamiltonian of the system will be just the Hamiltonian which can be exactly solved, the unperturbed Hamiltonian. So if we say that lambda is 0, we are considering just uh, that there is no perturbation in the system, and when lambda is 1, then if lambda is 1, then the effect of this perturbation is complete, right? So it is completely there. So it is just to define the strength of the perturbed Hamiltonian, right? So we can change this lambda to adjust this lambda by our choice, just to include the strength, how much strength we just want to include in the problem. So that is just a mathematical parameter. So if we consider that HP can be written in this particular form, then the Hamiltonian of the system can be written as H naught plus lambda W, right? So this is the Hamiltonian of the system that we want to solve the Schrodinger equation for. One more thing, because we have assumed that this particular unperturbed Hamiltonian has solutions, right? So it has eigenfunctions and eigenenergies. Already we can solve Schrodinger equation for this. So we suppose that the eigenstates uh, and eigenvalues of H naught are, so eigenstates are phi n, and the eigenvalues are, we are just assuming that they are represented by En naught, right? So if it is the condition, then we can write the Schrodinger equation for this unperturbed Hamiltonian. So if unperturbed Hamiltonian acting on these states will give us the eigen energies and the state vector itself. So this is another important equation. This is our assumption that this Hamiltonian can be solved exactly, and its solutions are these phi n, and the energy eigenvalue corresponding to this phi n is En, and there is a 0 on the upper side of the E. So this is the assumption that we have till now. Now let the eigenfunctions or eigenstate, whatever you want to call, and eigenvalues of the system that we are considering are psi n and En. Then we can write the Hamiltonian of the system if it is acting on the states that we are which we are assuming. It will give the energy eigenvalues and the state itself, or you can say it will satisfy the Schrodinger equation, time independent Schrodinger equation, right? Now the second assumption and the main assumption, and one more thing, let me just remind you that the the time independent perturbation theory that we are going to develop is for, right, for non-degenerate case. So for non-degenerate case, right? So this equation can only be written if we are assuming that these energy levels are non-degenerate energy levels, right? Because for these energy levels, if it is non-degenerate, then there will be just unique eigenstates. I will show you what will be the change in this particular equation when we will consider the degenerate case, right? So there will be an additional term alpha which will determine the degeneracy of the this energy levels. So in this case, we are just developing time independent perturbation theory for non-degenerate case, and this equation can only be written if we are assuming that the energy levels are non-degenerate. Right. So this is the one condition. Now the second and most important assumption in time independent perturbation theory for non-degenerate case is that we are assuming, this is the assumption, right? So this is the assumption that these states and these eigen values can be expanded as the power series of lambda. So it is the assumption, the important assumption. So we are assuming, we are assuming that the eigenstate, right, of the system that we are dealing with can be written like this as the power series of lambda. So it is just lambda power 0 into phi n, which is the unperturbed state, which we have assumed there, plus lambda power 1 into the first order correction in the wave function, plus lambda power 2 into the second order correction in the wave function, and so on, right? So it is a power series. You must have learned about the power series in your mathematical physics course. And also we are assuming that the eigen values of the system that we are considering can also be written in terms of power series of lambda. So it is En naught plus lambda square into En1, which is the first order correction in energy, plus lambda q, sorry, into lambda, and it is lambda square into the second order correction in the energy. So this is the second assumption in the perturbation theory. So these are the assumptions, right? So we have not started solving the Schrodinger equation for this particular system that we are considering. These are just the assumptions. So the first assumption was that the Hamiltonian, right? So the first assumption was the Hamiltonian of the system must be written in terms of this equation, where the effect of this particular term must be very small in comparison to this term. That is the first assumption. The second assumption is that the wave function and the energy eigenvalues must be written in this power series of lambda, right? Now you just have to do very simple calculation. You just have to put this equation into this equation number 4, this equation into equation number 4, and for this h naught, h cap, the Hamiltonian of the system, you just have to put this particular value, right? So let me write it properly because it will be a long equation. So the Schrodinger equation that we have to solve is h cap acting on uh, psi n, and there is eigen values into psi n. This Hamiltonian is h naught plus lambda or w, right? And these we have expanded terms of lambda, so it was phi n plus lambda psi n 1 plus lambda square psi n 2 and so on is equal to En, and again the eigen values we have expanded in terms of lambda power series, so it will be En naught plus lambda into En1 lambda square En2, right, into again this particular equation, which is for this psi n plus lambda into psi, sorry, it is phi n, it is psi n1 and plus psi square, sorry, lambda square into psi n2 and so on. Now let me tell you that this is the unperturbed eigenstates. This is the first order correction, right? So it is first order correction in eigenstates of the system we are considering. So in eigenstates, and this term is the second order correction, so it is second order. Why it is second order? Because it is just the coefficient of lambda power 2 and it is coefficient of lambda power 1. That's why it is first order correction. It is zeroth order correction because it is the coefficient of lambda power 0. So it is the zeroth order correction, which is the exactly soluble state. So you don't have to say it as the correction. Again, this is the exactly known eigenvalues, and these are the first order correction, right? It is first order correction in energy eigenvalues, and this is the second order correction, so it is the second order correction in energy eigenvalue, right? And what we have to do, we just have to calculate the first order correction in wave function. We will not calculate the second order correction in wave function in this particular lecture. And we have to calculate the first order correction in energy eigenvalues and the second order correction in energy eigenvalues. So these three quantities we are interested in calculating in this particular lecture, right? So it is very interesting and simple uh, calculation. So just let me write it again so that you can see it properly. So this is the equation that we have to solve. So it is just very simple calculation. You don't have to do anything. You just have to multiply these terms inside. So it will be like